I made a talk silly for you. I submitted it to EMPEX one time, then two. A meaningful concept it must be. Quote Dijkstra and surely they'll see. Oh wait, this sounds familiar. Quick telejoke lols are easily bots. It's much easier than leading any thoughts. Another food joke you'll have to make because intros are awkward and this is what it'll take. Also, side note, hot takes on hot cakes is probably the best hashtag on Twitter. Strong opinions on pancakes. You can't go wrong. So this is my actual talk. Here we go. Seussical faulting, indeterminate halting. And this is really a bigger talk that's about abstraction and the way we approach problems. And I kind of want to go about it in a really fun, interesting way. And I should introduce myself, although Desmond already did. I'm Bobby. This is my impronounceable string of characters that I go by on the internet. I like really simple slides. I'm sorry if my bland text and white backgrounds are boring. And I work at Wombat Security. I'm our lead Elixir developer there, and this is my fun little talk. So basically, starting off, if we look at the halting problem, it's a really classical problem in computer science. And at the core of it, there's a bigger question, and that is, are all problems decidable? And Kurt Gödel in the early 1920s, he did a ton of work and eventually drove himself to insanity, basically figuring out that if something seems complete, you can never prove that it's consistent. And if it seems consistent, you could never actually prove everything inside of it. And to a mathematician, this is obviously quite frustrating. So in 1936, a bit later, Alan Turing, working in sort of an analogous piece, proved the halting problem. And so Gödel had gone, no, things aren't all decidable. Turing goes, I agree tangentially. And this was a really big deal at the time. To basically be able to go, we can't figure everything out as humans that's unsettling, right? It's not fun. And so this was in 1936 that the halting problem was originally discovered. And about 50 years later, in 1986, a fellow named Jeffrey K. Pullum wrote a really, really, really fun proof. And what he did was he took the halting problem and managed to prove it in Dr. Seussical verse and find someone who was willing to publish that. And so what we're going to do now is we're actually just going to walk through the proof, and it's actually so approachable that you don't really... I was going to originally do this in IEX, walking through with some examples, but it actually seemed more approachable to go about it this way and sort of just walk through without those breaks. So without further ado, this is Scooping the Loop Snooper by Jeffrey K. Pullum. No general procedure for bug checks will do. Now, I won't just assert that. I'll prove it to you. I will prove that although you might work till you drop, you cannot tell if computation will stop. For imagine we have a procedure called P that for a specified input permits you to see whether specified source code with all of its faults defines a routine that eventually halts. You feed in your program with suitable data, and P gets to work, and a little while later, in finite compute time correctly infers whether any infinite looping behavior occurs. If there will be no looping, then P prints out good. That means work on this input will halt as it should. But if it detects an unstoppable loop, then P reports bad, which means you're in the soup. Well, the truth is that P cannot possibly be, because if you wrote it and gave it to me, I could use it to set up a logical bind that would shatter your reason and scramble your mind. Here's the trick that I'll use. It's simple to do. I'll define a procedure, which I will call Q, that will use P's predictions of halting success to stir up a terrible, terrible logical mess. For a specified program, say A once applies, the first step of this program Q I devise is to find out from P the right thing to say of the looping behavior of A run on A. If P's answer is bad, Q will suddenly stop, but otherwise Q will go back to the top and start off again, looping endlessly back till the universe dies and turns frozen and black. And this program called Q wouldn't stay on the shelf. I would ask it to forecast it run on itself. When it reads its own source code, just what will it do? What's the looping behavior of Q run on Q? If P warns of infinite loops, Q will quit, yet P is supposed to speak truly of it. And if Q is going to quit, then P should say good, which makes Q start to loop. P denied that it would. No matter how P might perform, Q will scoop it. Q uses P's output to make P look stupid. Whatever P says, it cannot predict Q. P is right when it's wrong and false when it's true. So where can this argument possibly go? I don't have to tell you. I'm sure you must know. A reductio, there cannot possibly be a procedure that acts like the mythical P. Just like fetch, it's never going to happen. I've created a paradox, neat as can be, by simply using your putative P, when you posited P, you stepped into a snare, your assumption has led you right into my hair. You can never find a general means for predicting acts of computing machines. It's something that cannot be done, so we users must find our own bugs. Our computers are losers. And I'd like to emphasize that our computers are losers. This isn't the computer's fault. It's largely everyone in this room. That's okay though. We try, and that's what counts. And no, seriously though, we broke a lot of computers. And Erlang fixed a lot of them, but we didn't realize it till 30 years too late. Everyone was doing this when they should have just bought into OTP. It would have worked way better. Now, and so if we think about what that proof was fundamentally doing, is like I was saying, it managed to abstract this topic that was basically world-shattering to the world of computer science in 1936. And 50 years later, someone was able to abstract that to the point that it was friendly and clever verse that a child could understand. And abstracting complex things in a fun way is really, really, really hard to do. It's a lot like if you're sending out a memo, you axe it until you get down to that distilled 3 sentences that you wanted. That takes an hour, but it takes 30 seconds to write the original, and this is that applied exponentially. And choice of abstraction is something that is very, 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 very important. And I think that the big thing with Elixir is that it's chosen very specific things compared to other languages. Ruby, how many Rubyists do we have in the room? So it's a good handful. Ruby, I think you guys would agree, is all about developers being happy. And I love that about Ruby. I still write Ruby for scripting stuff on a daily basis. If we go on and we look at something like SciPy and NumPy, which is an applied domain of Python, but it's purpose-built to be able to do very hard math very fast with linear algebra. That was the choice they made. That's what its use case is, and it's shaking the world. We look at things like TensorFlow being so accessible like they are right now. That was just previously unheard of. If you look at Haskell, it reinforces your inferiority complexes, or at least that's my experience. Troy was nice enough to recommend a book on Haskell that might not make me feel bad about myself, but I haven't had time to look into it yet. Or JavaScript, you just abstract the internet. There you go. You have the whole thing just in one single gzipped compressed file. It's the whole internet. But one of the biggest things when you're choosing an abstraction in a language and how you're building things up, I think, is the choice of what you want to be a primitive. And so a primitive, by a typical CS definition, I actually couldn't find. There's Wikipedia entries. There's some papers that talk about primitives. There's a lot of people who yell and talk about primitives, but there isn't a generalized definition. And from sort of looking around and gathering what I could on these academic and personal things, the best I could come up with is that it's built in the simplest unit of the language. And let's look at another language's choice of primitives to sort of paint how quickly something that is the simplest unit can become really, really hard. And anyone who's seen Gary Bernhardt's talk on JavaScript WAT, numbers in JavaScript, it's easy ammo. I like JavaScript, I'm not stabbing at it, but this is a very interesting example. So if we look in the this is from the ECMAScript 2016 specification. If we look at its definition of a primitive value in section 432, it's a member of one of the types undefined, null, Boolean, number, symbol, or string as defined in clause 6. Note, a primitive value is a datum that is represented directly at the lowest level of the language implementation. So if we keep going through here, we go down the 4 section that's kind of covering numbers. Now, from the number primitive, we now have number values, number types, and number objects. And how is a primitive an object? Okay, I can understand the type with it, but is a type also a primitive? Do we have typing here? And what do you mean by value? Oh, okay, IEEE 754 double precision floats, like that's reasonable. But there's a lot of other things that bring in questions here. And so if we go into the object part, the most confusing part of it to me, we can go in and we see, okay, so there's a number constructor, there's an intrinsic object, there's a number property of the global object, which sent me down another rabbit hole. There are a lot of rabbit holes defined here if you just want to dive into the ECMAScript specification and waste a week. But from here, so we go in, and now there's all these other things. Like there are all these little subclauses on like how these behaviors should work, and like everything that goes into how it should behave, and building on it more. And now we can construct them, and there's objects. And like the simplest building block of this just got really, really complicated. And that's not inherent to JavaScript. That's anything that where you are building up a large platform or a large service, it's going to be complex as you add things to it. That's just the nature of how things grow. And the thing that sticks out most to me about the Erlang approach that has been around is you can almost really think about a process as a primitive. Because if we look at the whole of how we try to work with Erlang, we aren't really thinking about processes or threads ever, really. It's all abstracted to a point where you might call a module that's using something like that, but your level of interaction, you're only allowed to shoot yourself in the foot so much as you want to. The edge cases are all covered. OTP has your back for these things. And like that just totally opened my mind and really made me think differently about how I approach developing things in Elixir and Erlang. Because once you realize that you're thinking about the problem to solve, and you now don't have to worry about concurrency. You don't have to think about fault tolerance. You aren't having nightmares about shared mutable state and thinking about an object that's getting properties from 5 boundaries away and you can't quite track it down. And this lets us concentrate on what we really need to build. And of course, Elixir isn't a silver bullet. We can't solve all the problems in the world with it effectively. But when you are solving the problems that are in its domain, there are a lot of built-in things that, because of that abstraction, offer us a ton of new things. We can go through and we can parallelize and isolate when we find bottlenecks. We don't have to do it by default, but the option's there, and it's not trivial, but it's not incredibly complicated to pull off. With umbrella applications, we can separate our concerns. We can have very clear boundaries between any part of the system, and it allows us to have these interdependent applications that can talk to each other very effectively, but allow us to separate those and have them handle themselves in an individual state. If we look at GenStage, you are never thinking about the idea of what you're actually doing computationally at the level of the processor when you're using GenStage. You aren't thinking about how this is being split up, how many workers there are, all these other things that are happening. You're thinking about the steps and not the throughput or what's going on under the hood because it works so well. And so basically, the biggest thing that I really have taken away from this is it's a famous quote. It's OTP makes some stuff really easy, and we should keep submitting conference talks about abstractions. Dijkstra-Gatesburg said this in 1847. And also, wasn't that a really cool paper? But that's really the main idea that I wanted to kind of talk about, is just turning the way you approach the language away from thinking about types and interactions, and think about actually solving the problem and using the sort of tools we have in the shed to be able to do this really effectively. And I know I'm about 5 minutes under. It seems I cut out a little too much worrying about going over. But I guess I don't know what would be Q&A, but since we have the time, anyone have random questions and answers? They can even be about grilled cheese. But if not, I know we're a little behind as well, so I can hop off and we can get on to the next awesome talk. So I don't see hands, but I'm also not wearing glasses, so I'm... Oh.
I have a question. Was that actually the entire paper that you read to us?
That was the entire paper, yes.
Congratulations for reading a whole paper to a conference.
Well played.